It can be a lot easier. Okay, so let's assume that we are done with the foundation work. So I still have one more example to give before we go into your AS question. Um, let's look at this one as well. N2O4. It's a gas. Reversible arrow to give you 2NO2 is also a gas. The color of N2O4 is pale yellow. Pale yellow. The color of NO2 is brown, orange. No, is reddish brown. So we have reddish brown gas. The forward reaction require just heating, and the backward reaction require cooling. So when you cool it, it goes backward. Okay, so look at this now. So you are supposed to know this reaction ahead of your exam. That N2O4 is pale yellow, NO2 is reddish brown. They are popular gases, especially NO2. When you do the composition of nitrate, and when you do yes, when you do thermal decomposition, how to explain that, they will tell you NO2 is a reddish brown gas. Okay, so that is one of the observations. When nitrate decomposes, it gives you a reddish brown gas. So NO2 is always a reddish brown gas. But N2O4 is not very common. It's pale yellow. Okay. They will now ask you what happened when heat is applied to N2O4. What happened? What will be the effect of what happened to the position of equilibrium? Or describe
It will move to
describe what happened.
the right.
Okay, so position shift to
It
the
will move
right.
to the
Okay,
right,
yes.
and more of NO2 is produced.
Okay, in terms of now, color now.
The mixture will become, or like the substance will become reddish brown,
Okay, good.
more reddish brown. The
Uh,
pale yellow fades.
uh, uh, the same thing happens when you cool the reaction. The reverse will happen. So the position of equilibrium shift to the left hand side. The reaction mixture become pale yellow, which means that reddish brown color will fade away with seeing pale yellow because they are both gases. So the whole mixture become pale yellow and no longer reddish brown. And then there is more of N2O4 produced. So that is about this kind of color changes in aqueous reaction. Now let's move on. Let's go to the slide now, and then let's see the next question. Next one. Um, okay. Let's see this one. Let's take more. Let's take that is concentration. Let's go to temperature. Temperature change, and I have already said that temperature is the only factor that can affect the the value of Kc. Oh, that is just temperature. And talking about temperature, there are two things that you must consider. You must consider whether it is exothermic, that is delta H is negative, or delta H is positive. That is what you look for. If delta H is positive, it means that the reaction requires input of energy from the surrounding. Delta H is positive, is endothermic, it requires input. So an endothermic reaction is a reaction that requires energy. before you can start. So you must add energy. So increase in temperature will simply move the position of equilibrium to the right-hand side for endothermic reaction. So the first question here, this one, the delta H is positive. So when you increase the temperature, the system, the position of equilibrium will shift to the right-hand side. More CO and H2O will be produced. But when the temperature, when the reaction is exothermic, delta H is negative. What it means is that the reaction is producing energy or is releasing heat to the surrounding. So it does not need heat to go forward. So when you increase temperature, it will be a backward reaction. Equilibrium will shift to your left-hand side because the reaction the Kc has to remain constant. So adding extra heat or extra energy or increasing temperature will be backward reaction because it does not need heat at all to go backward. Why? When you increase temperature, the product will decompose and form reactant. So when delta H is negative, you don't add temperature. What you do is to reduce. For you to have a forward reaction, you reduce the temperature. So increase in temperature does not favor forward reaction for exothermic reaction. So that is very, very important. So what I have here is a summary of what I'm saying. When it's exothermic, equilibrium will move to, when you increase temperature, to the left. If you decrease temperature, to the right for exothermic. But endothermic, that is positive. If you increase temperature to the right, and if you decrease to the left, so it's both ways. It's both ways. I hope this one is clear.
Yes, sir.
That is very, you can have issues with that, increasing and decreasing and the rest. So we'll just move on to the next, to explain catalyst. Catalyst is a substance that increases the rate of reaction by what? By decreasing the activation energy, by lowering the activation energy. That's catalyst. It increases the rate of reaction by lowering or decreasing the activation energy. Or simply put, a catalyst is a substance which provides an alternative reaction pathway by lowering the activation energy. So this is always 2 marks when it comes out. It speed up the rate of reaction by lowering the activation energy, or it provides an alternative pathway with a lower activation energy. So to explain that, we often use the Maxwell-Boltzmann distribution of molecular kinetic energy. The Maxwell-Boltzmann distribution of molecular energy. So in a reaction, the reactant do always have what I call higher activation energy. So when the activation energy is very high, they only collide and then no reaction, because their collision does not lead to producing the minimum energy called activation energy. Activation energy is the minimum energy required for a chemical reaction to occur at the minimum energy. So when a reaction has higher activation energy, collision does not lead to chemical reaction. It simply bounces back. So the whole of this place, they are full of molecules with higher activation energy. No reaction. So only this place that contains that molecule will have that contain the molecule that have the required EA to react. Only this place. So when you use a catalyst, the catalyst will reduce the amount of energy required. So you can see so extra molecule with sufficient energy overcomes the energy barrier. So when you bring in a catalyst, the catalyst will lower the activation energy. So we have a new EA. Let's call the first. This is the EA1. They will now have this one EA2. EA2. So EA2, they have more energy that is equals to the EA or more than EA, equal to the EA or more than the EA for reaction to occur. So this graph is very important. Okay.
Sorry, sir, can you explain the EA2 and the EA1 again?
Which one is that? The
EA2 and the EA1. I didn't get
okay.
that.
Yeah. Now the EA1 and EA2. The EA1 is the graph of the reaction that occur without the use of catalyst.
Okay.
Without the use of catalyst. So the moment you add a catalyst, it lowers the energy because the X-axis is talking about energy. So if the X-axis talks about energy, therefore the EA, the EA1 is the activation energy without a catalyst. The moment you bring in a catalyst, it provides an alternative pathway which lowers the activation energy. So it's moving from EA1 to EA2. We have here EA to EA2 is lower. So the moment the EA has been lowered, it gives room for more molecules to have the required energy for collision, for reaction to occur. And so you can see that this place now, this is when EA has been reduced by the use of catalyst. So, but this graph is different from temperature. The temperature, we have two different types of graph on the same X and Y axis. But for catalyst, it's only one graph, but there will be two bars. There will be two bars. The first bar is talking about the higher EA. Second bar talking about the lower EA. Be sure that the first bar is higher. The bar that is higher is the EA1. The bar that is lower, or the broken line that is lower, is the EA2. EA2 is the one that has catalyst. So you must know, because they ask you to identify which one is catalyst, EA1 or EA2. EA2, or the one that has to do with catalyst, is always lower than the other one without catalyst. That
Isn't EA1 lower than EA2?
it's not possible for EA1 to be lower than EA2. But EA1 and EA2 are labeled, so they can change the label. But you must know what we are supposed to know is where is the EA itself. Where the two bars, there are two broken lines there. So the first broken line is higher. This is the first broken line, this one. This one, the first broken line. That should certainly be EA1.
Oh, okay. It's going from left to right.
Yeah.
Oh, okay. I was looking from right to left.
So the EA1 is always up. is or always on the right hand side, more on the right hand side, more on the right hand side. Then the EA2 is closer to the left hand side more. So the EA2 is the one that has the lowest energy. So even though they change the label must be the same. EA1 without catalyst, EA2 with catalyst, simple like that. So, but if they put EA2 in the front, in case they put it in front, because these people, they are very terrible sometimes. So you can say this one is your EA2 and this is your EA1. It means that EA1 is the one with catalyst. That's simple. So the labeling can be different. But you must know that the one that has the lowest energy, you look at the energy. Towards the left hand side, this is energy. This is the arrow for energy. So the energy, this one is at lower energy than this one. So the one with the lowest amount of energy is the one with a catalyst. So that is key. So the Maxwell-Boltzmann, the kind of molecular kind of energy, it can be used to explain how catalyst is used to reduce the EA. That is one. Under temperature, I did not explain the Boltzmann distribution of energy. For that one, if you have a reaction, if you have a graph like this is like that is a graph. This will be the fraction of molecule that has the required EA. So this is EA. That one has only one EA, like that. So this area that is shaded represent the fraction of molecule. And of course, and this is your energy. Okay, and this is your number of molecule that take part in the reaction. And this first graph is showing the temperature T1. So if you increase the temperature, more molecule we have Ke. That's the first one. If we increase temperature, more molecule we have Ke. Number two, there will be increase in collision frequency. Collision frequency increases. Number three, molecule will have EA or more than EA for effective collision. So once you increase temperature, there is every possible likelihood that the Ke will increase, sure. Frequency of collision will increase, and then more molecule will have EA. To show that you don't draw another, it does not involve EA, you draw another graph. That graph will not be like this to show this first graph is showing you the area of molecule. It's showing you two areas. The first area here, this one here, they are the molecule with higher EA, no reaction. Only this one have the required EA to react. The molecule here have EA or more than EA for reaction. The molecule here, they have no EA. Your EA is lesser than the real EA. Their EA is lesser, so no reaction. So the moment you increase temperature, the fraction of molecule with EA will increase. And how do you show that? This is how you show it. So it will be like this. So this part, the molecule here now have been moved down to this place. So more molecule now have EA like that. So therefore, the second graph will now be T2, where temperature T2 is higher than temperature T1. So you can see the shading now. So it requires only one broken line, this line. Now they both have the same EA, but more molecules are added. The shape of the graph changes. So there are two graphs. The first one, higher temperature. The first one, lower temperature. T2, higher temperature, moving more molecules to the right-hand side. So temperature deals with two different graphs. One is steepy, the other one is slopy. It convinces students or confuses students a lot. That is about that. They will not ask you, state the effect of the second graph. Second graph, or you draw a graph. So that you draw a graph like this to show, and you now shade it very well. The upper part, so there are two layers now. The first layer is one without which is lower temp. This is a lower temperature T1, and this one is higher temperature T2. That is for Boltzmann distribution of molecular kinetic energy. While this one is also Boltzmann distribution for molecular energy using catalyst. This one is for just temperature for that one. Now, coming to the second graph, which is this one. Whenever you use a catalyst, it lowers the activation energy. So in this place now, in this graph, you will see the normal reaction in broken line. The normal reaction starts here and ends here. The one catalyzed also starts at the same place and ends at the same place. They both have the same delta H. But the difference between the two is that the one without a catalyst have a higher EA. The EA of that is this one. That is the EA. EA without a catalyst. So, but the one with a catalyst is the one that goes via this one like this. So, in this reaction now, there are two punch bags. There are two EA. The first EA, second EA, meaning that in this reaction, there are two intermediate processes. In a given reaction, there are you can have, for example, now carbon, for example, carbon plus oxygen to give you carbon dioxide can have an intermediate like carbon plus oxygen will give you carbon monoxide like this. So this is the first intermediate one. Then second one, in second reaction will be CO plus more oxygen. This is the product used plus more oxygen will give you CO2 like that. So okay, look at that. So there are two intermediate. So what the first intermediate, this one, will be for this one. Second EA is for this one. So the overall two intermediate reaction equals to this one without a catalyst. So the broken line is a reaction representing carbon plus oxygen to give you carbon dioxide. No catalyst. When you now use a catalyst, it will not be the other two intermediate lower with lower activation energy. So it will be the first one, second one. Then we give you the same product, because if you cancel 2CO with cancel CO, then C plus O2 gives CO2, like that. Okay, so overall reaction is the one without the broken line, but the other two represented in a smaller intermediate. So it's very important. Now, what are we talking here now? Clearly, in a catalyst, you can see that the overall EA has been reduced. This is the EA, but when you use the catalyst, the EA has been broken down smaller one, so it is faster. So another pathway has been created. So a catalyst is a substance that increases the rate of reaction by providing an alternative pathway with lower activation energy. I don't want to waste too much time, but this reaction SO2 plus O2 to give SO3 is also a good example that have two different intermediates. So maybe when I'll be talking about this more of a Maxwell-Boltzmann distribution, or when we get to sulfur, I will talk about this reaction. It will have two different smaller intermediates. And of course, you know that this reaction have V2O5 as a catalyst. So the first reaction does not have a catalyst, which is SO2 plus O2 to do SO3. That will be this one. Second reaction is when you use V2O5 to give you the smaller EA, because we have SO2 plus there is I don't want to put it now because it takes some time. So that's about that. So the purpose of this graph is to let you know that catalysts provide another pathway with a lower activation energy. That is about that. But now, to leave this slide now, you can see the overall energy, delta H, is always the same, whether catalyst is used or not. Enthalpy change is the same, except one is faster than the other. The one with the catalyst is faster. The one without a catalyst is slower, but the same enthalpy change. Okay, so let's move on. So I have explained all of this one, but finally, adding a catalyst does not affect the value of Kc. That is what this is talking about. Adding a catalyst do not affect the value of Kc. So Kc remains the same. What changes is the position of equilibrium, or the speed of reaction rather. The catalyst will make it faster to reach equilibrium, to get to equilibrium. That is that. So let's look at application of
Catalyst.
yes, of what we have learned now. Temperature, pressure, and catalyst put together on Haber process. Haber process is a process used to manufacture ammonia in the industry. Haber process is a process for the manufacture of ammonia in the industry. So in the Haber process, you are supposed to know the correct conditions. The correct conditions are conditions that are compromised. Compromised in the sense that if you use the normal condition, the reaction will be either too slow or too fast, the owner of the company will not be able to make profit. So the condition given to us here of 200 atmosphere, which is equals to 20,000 kilopascal, is a compromised condition that makes the manufacturer of ammonia to make profit. The actual pressure is not 2,000. So it's a compromised pressure. Now, I did not explain pressure in this slide, but I will explain pressure right now together with this one. When you increase pressure, you consider number of moles. If the number of moles of a reactant are higher, in this one now, there is 1 mole here, there is 1 mole here, and 3 moles. So overall mole here is 4, and here is 2. This is so higher. So more moles, more pressure. So what this one is telling us is that the forward reaction requires higher pressure. Higher pressure. Why? Because there are more moles on the reactant side. So if we move forward to balance the moles on both sides. So what you consider under pressure is number of moles on both sides. The side having the higher mole, if it's reactant, forward reaction. If the side having the higher mole is product, it means that increasing pressure will be backward reaction. Equilibrium position will shift to the bar, to the left-hand side rather. So that's about pressure. So you must master that one. So ammonia, there are more moles on the left-hand side. So when you increase pressure, it will move forward. And if you lower the pressure, the backward reaction, because the forward reaction requires higher pressure. That's about pressure, which is very, very important. Okay. Now, to explain this slide now, like I said, that the 20,000 kilopascal or 200 atmosphere is compromised, so that the owner of the company can have an economic gain, it can be economically feasible. Temperature is 380 to 450 is also a compromised temperature. Why? The reaction is already exothermic. Delta H is minus 92 kilojoules. So if you increase temperature, it will go backward. So the temperature has been partially reduced. So 450 to 500 is manageable. In your textbook, you will see 450 to 500. Anything above this one cannot work. It will be backward reaction. Anything above 500, ammonia decomposes. Ammonia decomposes and form product. So under question on the ammonia like this, they will test you on rate. They will test you. I'm coming, please. Okay, I'm back now. My wife was asking for some money to buy some items. So sorry about that. Okay. Are you still there?
Yes, sir.
All right, good. Now, so like I said, so if you enter above 500, ammonia decomposes. So under this question, this slide, they'll test you 2 things, and it's confusing. The rate of reaction, and then the yield of the reaction. So now they will say at 500 degrees Celsius, explain, if any, change the effect of increasing temperature on the rate of reaction and on the yield of the reaction. One is exothermic, and you know that the maximum is 500, and above 500 now, like maybe 650. It has been moved to 650 now. So being at 650, what will be the effect on the yield and what will be the effect on the rate of reaction? Let's talk about the rate first. At higher temperature, rate increases. Rate increases. But the increase in rate will be negative. Once the temperature is 650, ammonia decomposes. So rate of forward reaction will increase, backward reaction will increase. But the effect is that ammonia decomposes to form product. So the rate of forward reaction increases. So more ammonia will produce, but it decomposes. So rate of the reaction will increase. So technically speaking, this rate of backward reaction that will increase, not forward reaction, because ammonia is decomposing fast at higher temperature. So rate of reaction increases, ammonia decomposes and produces nitrogen and hydrogen. So at higher temperature, the owner does not make profits. So at 650, the reaction rate increases, ammonia rate increases, but not for the forward, even though for both reactions, but the forward reaction is not working because ammonia is decomposing fast to produce hydrogen and so rate increases, and more ammonia decomposes to produce hydrogen and nitrogen. That's one. Then on the yield of the reaction, since ammonia decomposes, the yield of ammonia reduces at higher temperature. Yield reduces. That is that. So if they also want to pull your leg, they tell you what happened at 300 degrees Celsius. 300 is below 450, 550 allowed value, allowed compromise value. At 350, the rate will be very slow. Rate because it's lower than the normal recommended rate, so it will be low, reduction will be very slow. So ammonia will be produced at a lower rate. So yield will be lower. It's not economical. So the only economical temperature is between 450 and 500, even though this one is saying 380. This slide, no problem. 450, 500 is allowed. You see that in your syllabus. That's about that. So at low temperature, higher yield, exothermic reaction, higher yield at lower temperature. And all. So that is what I've got trying to explain now. So now let's look at pressure. I've explained temperature right now. I've also explained, let's look at pressure now. Pressure at 200 atmosphere, normal forward reaction, the owner will make gain. But if pressure is like 1.5 atmosphere, that's lower pressure, the forward reaction will be very slow. There will be more backward reaction. There will be more backward because it requires I mean 150 atmosphere ATM, not 1.5. So now, so at 150 ATM, below 200 atmosphere. So backward reaction will occur, and so the yield of ammonia will reduce. But if you make it like 300 ATM, 300 atmosphere, 300 atmosphere, higher pressure, Let me hear from you. At 300 atmosphere, what happens to the rate of reaction and the yield? Let me hear from you first.
I think when there's a higher pressure than 200, the molecules of NH3 will reduce, and so like there'll be yeah.
Okay, no problem. At higher,
Does that make sense?
yeah, I understand what you are saying, and I can understand your predicament too. Now, at higher pressure, the forward reaction, there are more mole here and there are lesser mole here. So it favors the forward reaction. So more ammonia is produced. At higher pressure, the hydrogen and nitrogen are closer because the pressure will make them become closer. So they will be more closer, there will be higher collision. So rate will increase, yield will increase, but it has one disadvantage. The affordable pressure is 200 that the owner can afford. The pipes that will carry 200 will allow the owner to make profit. The pipe that will carry 300 atmosphere will not give room for the owner to make profit. The profit that will have been made will have been consumed in making pipe that can hold a pressure of 300 atm. So a pressure of 300 atm will increase yield, will increase rate. Why will increase rate? The molecules are closer together, and so higher collision frequency, faster rate. Why will it increase yield? One that is a forward reaction, so ammonia will be produced faster at that. But the disadvantage is that no profit, because the pressure to hold 300 atmosphere, the pipe that pipe is expensive. The pipe that will be able to hold a pressure of 200 is highly expensive. It is not economically feasible. That is the problem. So they want you to know what's going on in the industry, that the 200 atmosphere is a compromised atmosphere. You're going to ask, explain why is it a compromised atmosphere. You not tell them that above 200, like 250, it will be too expensive. It is not economically viable. Below 200, the forward reaction will be too slow, also not economically advisable. Ammonia will not be too much, so there won't be profit. So the only pressure where you can have profit is 200 atmosphere or 20,000 kilopascal. Above that, it is too expensive to maintain, no profit. Below that, lower yield, and the owner will not make profit. That's about that. I've also explained temperature and pressure. So catalyst, the catalyst must be finely divided. Finely divided. What does it mean? So it's finely divided.
They're in like they're not in chunks, like they're in pieces, like yeah,
Yeah.
tiny particles or yeah, something like that.
All right. Powder. It means to be in powder form. So in powder form. Now, I did not mention something about catalyst. In your A2, okay, they have brought that one to your AS now. Types of catalyst. Now, this reaction of this Haber process, it require ion catalyst. Ion catalyst is solid. You will see that the reactant and product are all gases. When a catalyst is in different state to the reactant and product, we call that one heterogeneous. heterogeneous catalyst. That is a catalyst that is in different state compared to the reaction. All are gases, but they are using solid ion catalyst. We call that one heterogeneous catalyst. But when the reactant and the product and the catalyst are in the same state, we call that one homogeneous catalyst. Homogeneous catalyst. So hetero means different state. They use the word phase. That's what they use. When the catalyst and the reactant are in the same phase, homogeneous, like the same. Hetero is when the catalyst and the reactant are in different phases or states. Hetero. So give us, they ask you what type of catalyst is used. Heterogeneous, because it's solid. It's not the same phase as the reactant. Therefore, heterogeneous. So we have other reaction that will require there is a reaction in A2 chemistry that talks about I can't remember the reaction. S2 O S2O is 2 minus plus Br, not Br now, plus I minus to give us S4O is or S4O is 2 minus plus I2. These are aqueous. They're all aqueous. They're all aqueous. Now, this reaction, you will see that it does not occur. It is look at the charges very well. -2, minus, it's also minus. So they are all negative. Both the reactant are negative. So there is no way we can bring in two negative reactants together. So what they do is to bring in a catalyst, Fe 2 plus and Fe 3 plus. They are both aqueous. So you will see that this catalyst is the same phase with the reactant. The reactant S2O6, 2 minus, and I minus, they are both aqueous. And the catalyst too aqueous. So homogeneous catalyst. This is homogeneous catalyst. So when you bring in this reaction, you are saying that Fe is 2 plus. It will catalyze it will allow S2O O6 2 minus to form S4O8. While S4O8 we also react with iron 3 and bring it back to the other one. So this reactant, what I'm really trying to explain to you is that the catalyst iron 2, iron 3 is the same phase with the reactant. So it's homogeneous catalyst. So that's very important for that. Okay, so we can talk about examples now. Okay, important uses of I think we'll be okay. Can we stop? Where can we stop?
The time.
Is it 11:35?
What do you think?
And if you want me to stop by 12, no problem.
Or because like I'm actually leaving the house very, very soon.
By what time?
That's why I need to ask my mom because well like we have an appointment at 1 o'clock.
Okay.
So
So you can leave your house
um
by after 12. Abi?
sorry?
Can you leave your house by 12 o'clock or after 12?
I'm leaving my house like before 12.
Okay. So when do you want us to stop exactly so that I can know what to do now?
We can stop at this place. Like you can go through it, then we can stop at this place.
Okay. Okay. All right. So let me round up now. So let me round up. So this slide is talking to you about ammonia and its compound. The ammonia is used in making ammonia fertilizer. Ammonia is used in making nitric acid. Ammonia is used in making explosive like TNT. TNT is tri nitro tri something tri nitrophenyl something. So TNT. Then ammonia is used in making nylon. Okay. So we have some examples. All right. So the example will be next class. The example will be next class. So we'll stop here. Okay. So tomorrow we'll continue. But you said tomorrow we will do what now? We'll do organic reaction, right?
Yes, like bond fission.
Okay.
Yeah,
Your organic reaction like
like homolytic and heterolytic reaction.
okay, okay, I understand. So we'll talk about that one. So don't I will send, can I send you question on calculation of equilibrium concentration, or
Okay.
we should do an example before we send a question?
You can send me questions.
Because since it came out in the exam, um,
You can send me questions.
okay, okay. So I will try to send, I will send you the question, and then I will see your response, and that is very, very important. When I see your response, we'll find out. So let us stop here. I think you have learned something.
Yes.
So which means that next week Thursday, we will now stop question on different type of question on equilibrium constant, Kc and Kp anyhow. So that will be that. So let me end the class, and then
Okay, thank you, sir.
yeah, so I wish you all the best. So,
Thank you.
yeah, so enjoy yourself, enjoy your class. So bye for now.
Okay, bye.
Yeah, all right. So I will send you the other material.